All right. So, as you know, I'm talking about vortices as probe for phase transition. If you are thinking something like BKT, that's not really what I am going to talk about. So it's not going to be difference between two phases where in one side you have vortex proliferation, on the other side you don't. So really, I'm going to use a single vortex as a probe in both sides of the phase transition. That's what I'm going to do. Also, as of now, this talk does not have much to do with turbulence, but I would like to know if there is any interesting problem that can be done or thought about. So, so with that, let me go into the details of the talk. So, let's say we want to understand phase transitions. So here is the standard approach, which is the Landau paradigm for phase transition. So you have a parameter which you are dialing to go from one regime of the parameter space to another regime. And you have a Lagrangian, which is invariant under a certain symmetry transformations in both regimes. And let's say your ground state breaks the symmetry in one regime and doesn't in another. So you can then say for sure that the two regimes are separated by a phase transition. So that's the Landau paradigm. So this is a theorem, right? Now, here is the paradigm for continuity. This is not a theorem. This can at most be a conjecture. So again, you're dialing a parameter. You have potential that's invariant under symmetry, a particular symmetry transformation in both regimes of parameter space. And then let's say your ground state is either invariant under the symmetry transformation in both regimes, or it transforms under the symmetry transformation in both. So in both of these cases, you can make a conjecture that the two sides are smoothly connected without a phase transition. So that's what the Landau paradigm is. Now, there are certain scenarios where Landau paradigm doesn't quite work, okay? So one of the examples is superconductors. So you have a U1 gauge theory, so electromagnetism, and then you have a condensate, a charged condensate of Cooper pairs, let's say. So below critical temperature, you have Cooper pairing of two electrons. That means that there's this two electron operator, which you can write as a bosonic operator, scalar field, that has a non-zero vacuum expectation value. And then above critical temperature, the same operator does not have a vacuum expectation value. Right? So there is Cooper pairs basically break up above critical temperature. Now, one could use, this object phi, the scalar field, to comment on the phase transition. But really, it's not a legitimate thing to say that, that the fact that this phi picks up a non-zero vacuum expectation value can be used to detect phase transition, because this object is not gauge invariant, transforms under the U1 gauge transformation. So that's why there are no local local legitimate order parameters that can tell you the difference between superconducting and non-superconducting phases.
Why is it necessary to be gauge invariant?
Because if it is gauge dependent, what does it mean to say that the two sides are separate?
But magnetism is like this. It's invariant under rotation. See, that's basic two group, or all three group you call, but you can consider rotation around a single axis. It will be similar to this.
Is that a gauge symmetry?
Well, you see, you can call it a J rotation. You see, group rotation, you can call it a gauge symmetry too. You can make it local even. So I don't know why not. So I don't know why you need that.
So gauge. So that's one issue. So the point is that if you there was a paper by Calvin Raymond, I think that's one point. It said that gauge symmetries cannot spontaneously break, so it doesn't make sense to talk about gauge dependent objects as an order parameter. So I will show you actually one example, which is particularly relevant for QCD.
Okay, yeah, it's not clear. Anyway.
So yeah. So what we need is, number one, a gauge invariant probe. Number two, it has to be such a gauge invariant probe whose expectation value jumps at the transition. So it has to be a discontinuous.
This first order, right? First order transition was second.
Or a kink.
Yeah, or a kink.
I'm sorry?
Or a kink.
Right.
Well,
So if it's gauge invariant,
when you
then
have
it
a
will be
kink,
second order.
when you have a kink, you have derivative, which it's sharp jump. You see, so kink is not the same thing. That's continuous. A kink is continuous. The derivative is not continuous.
Right. So I mean either that or its derivative. Okay.
Right.
So something has to be discontinuous. That's right. Non-analysis. That's what I.
What?
But very
Right. That's a particular definition. It's a restriction. You want to do it that way. That's fine.
Right.
That's the way it leads you to.
Well, so
But anyway.
what? Okay. So long as you find other ways, that's fine. But I'm just saying that this is not.
No, it looks to me like you're painting yourself into a corner. You see, you see, I'm going to do it only this restricted things, phenomena called phase transition or the parameter. So you restrict the class of all the parameters.
I am excluding anything that is gauge dependent. That's all. Okay.
Why?
So that's what I need. And if I don't have a jump, non-analyticity, I don't know how I can detect phase transition. So for now, that's what I can rely on. So one idea would be, let's say you have magnetic flux tubes inside superconductors. You have like vortices, which have quantized fluxes in them. And so below critical temperature, you have flux quantization. Above critical temperature, you don't have that. So maybe one could use this to detect or use this as an order parameter. So how would you do that? So one way you could do it is to look at Aharonov-Bohm effect.
Well, flux, it's a vector.
Yeah.
So it's like magnetization. So you see, you go back, you see to the same thing. So that's the same thing. It's magnetization.
It's not.
Sorry. It has a direction.
No, it's not you.
So there isn't left corner close. Okay.
It's a touch sense of the screen, so when you hit it with the.
Right. Okay, I won't. Okay.
So I don't see the big difference.
But hang on, magnetic fields and electric fields are gauge invariant.
Yeah.
Right?
What do you call gauge? You call the gauges in the vector field,
Yes.
or you call the rotation like magnetization? The rotation is a gauge field too. I can show you. You can do it in classical physics. I'll give you a long article.
I will give an example where you wouldn't be able to detect the phase transition by looking at gauging. In fact, there was the
Well, it's
conjecture.
not clear why you need that.
Okay.
Come back.
All right. So here is the standard Aharonov-Bohm effect. You have a coil, a solenoid through which you're sending current, let's say, and then you have a magnetic field inside. And if you shoot an electron in such a way that the electron wave function does not penetrate inside the coil, and on the other side you put a screen, you will see that there is an interference pattern, which will correspond to a phase shift between the two paths that the electron could have taken to reach the other side of the screen. Now, this is the standard Aharonov-Bohm effect, and the Aharonov-Bohm phase is actually proportional to the amount of magnetic flux that is inside the solenoid. And you can compute this magnetic flux by taking a line integral of your gauge field around a path that encloses the solenoid. Now, this object, or the Aharonov-Bohm phase, is a gauge invariant quantity. That's why it's observable. Otherwise, it wouldn't be observable. So the key feature of this object that I'm going to deal with, it's the exponential of I times the line integral of the gauge field. It's gauge invariant, and the second feature is that it's non-local. So that's that is what is going to be important in my next slide.
What does it mean non-local in real life?
So what it means is that it depends on, it's the operator is not at a particular point, right? So you have to go do a line integral to get to this.
No, but that's the integral. It's not local method.
Yeah.
But after you perform the integral, you see that that's a number.
Sure. Yeah.
So it doesn't have coordinates or anything.
That's fine. Yes.
But it depends on multiple points in space.
Right.
What?
It depends on multiple points in space.
So that's the energy of the system.
Right. So
So
the energy is
almost
not
anything
local.
you know, you see.
But the energy density doesn't. That's
No, it's just a topological
Yeah.
property.
It's a
right?
topological property.
So,
Yes.
is what you're saying essentially about this transition being particular? Is it just to say that the superfluid transition is in nature a topological transition, that local problems in order to code for that? The two-dimensional case, for instance, is a good example, right?
Right.
Where nothing changes locally for the system. There's no long-range order.
Yeah.
No order parameter, but topologically the system has superfluid response.
Right. Exactly. The thing with the superfluid transition in 3 dimensions, 3 plus 1 dimension, one-time dimension, is that there is a local order parameter there, which is the condensate that we lose in this case.
Mm-hmm.
And in the case of superconductor, it's really not going to be, it's not going to make a big difference, but there is another situation where it will. So I'm just setting up the story for that. So let me quickly recap ordinary superfluid vortex. So here, the vortex axis is along z-axis that's coming out of the board, and the superfluid is going around the z-axis. Let me call that some azimuthal angle theta. And of course, there is the macroscopic wave function psi that characterizes the superfluid. And if I wanted to write down the energy density of the superfluid, I would have to remember that it doesn't like undulations in its profile. So the energy density, that's why it goes as gradient psi mod square. Now, if I wanted to compute the energy density of the superfluid, I would have to write an ansatz for the psi, by the way, which is in this case a neutral object because it's a superfluid. So as you know, far away from the core of the vortex, the distance here I'm denoting as little r, so it's a radial distance. So the magnitude of the condensate far away from the core of the vortex is fixed, it's constant, doesn't have radial profile, but it goes as e to the I theta. It completes a single winding around the z-axis. So if I substituted that here, I would see that the energy density of the vortex goes as 1 over r squared. And so energy per unit length is logarithmically divergent. So that's the standard vortex story. Now, here is the corresponding story for superconductors. So now the superconducting vortex axis is along the board going upwards. P is the path along which the vortex axis is aligned. So again, along the theta direction, the supercurrent is going. And there's going to be a magnetic field inside the core of the superconducting vortex. And what I want to compute is the Aharonov-Bohm phase corresponding to that flux-tube. So C is the path along which I'm going to compute the line integral. So as you know that the superconductor is given by a 2-electron Cooper pair. So this psi now has charge 2, right? So if I wanted to write down the energy density, I would have to replace just the gradient by the covariant derivative of electromagnetic field. So that's what I have done here. The 2 comes from the fact that this has charge 2. So that's why there is a 2. Now, what I want to do is I want to write down the ansatz for the superconducting condensate. And then I want to find out what the gauge field is doing far away from the core of the vortex. And to find that, I have to minimize the energy density, right? So the ansatz for the condensate is the same as what it was for superfluid. On top of that, I have to give you the ansatz for the gauge field as well. And here is the right ansatz. It points along the azimuthal direction, goes as 1 over r. B is a parameter with which I parameterize the gauge field. And now if I substituted in the energy density and tried to minimize, I would see that B equals half minimizes the energy density. And this too comes from the fact that you have a 2 here. So that's what is appearing there. And the energy density of these vortices go to 0 far away from the core of the vortex. So these are really local vortices and not global vortices. And if I now compute the Aharonov-Bohm phase, I'll get a factor of pi. Okay. So this Aharonov-Bohm effect is being felt by an electron, which is half the charge of the Cooper pair.
So what you're doing in case of a neutron superfluid, like
Yeah, that's what I'm going to talk about eventually.
They don't have a gauge field.
I will come to that. That's the whole point of the talk. Okay. So there are some consequences here. Number one is that, well, I'm just capturing the flux quantization through these Aharonov-Bohm phases for the electrons. So you can interpret this as a fractional statistics between particles and vortices. Above critical temperature, there is no quantization, and so there's no fractional statistics. So you can say that omega, or rather the derivative of omega, sharply jumps across the transition and can serve as an order parameter or a probe. However, for superconductors, one didn't really need this because there are other ways to detect a phase transition. One of them is to just count the number of massless modes on either side. On one side, which is the superconducting side, the theory is completely gapped. So you don't have any massless modes. On the other side, you have photons. So the number of gapless modes don't match. The other thing that you could do is to compute the free energy explicitly and see that at the transition, there is a sharp jump. So that calculation is under control and you can do it. Of course, none of these are equivalent to having a legitimate order parameter, but however, these are sufficient to detect phase transitions. However, the concept that I just discussed, that is flux tubes and vortices, will be handy in a different scenario in dense nuclear matter and quark matter. Okay, so that's where this is really going to help. By the way, whatever I discussed in terms of these using these as order parameters, this was actually first discussed in a paper by Shivaji Sondhi, Hansen, and Ovanesyan in their 2004 paper, where they said that superconductors are topologically ordered in the standard sense of topological order. Okay, so this is the phase diagram of quantum chromodynamics, which is what I'm going to concentrate in the rest of the talk. So as you know, this is something that nuclear physicists spend a significant part of their time thinking about. So I'm going to concentrate on the low temperature, high density part of the phase diagram. So instead of looking at this detailed phase diagram, let me go to a cartoon, okay? So this is the phase diagram for 3-flavored, 3-colored quantum chromodynamics. If you are not sure about what I mean by that is that, so QCD is a SU3 gauge theory. So on top of that, you have fermions. There are 9 types of fermions. Every single fermion comes with a degree of color, a degree of freedom that's flavor. So red, green, and blue quarks, and then up, down, and strange flavors. So there are like 9 types. Okay. So let's say, so what I'm doing here, so what this diagram is telling you is the following. If you take a chunk of matter and either crush it to extreme densities or take it to extreme temperatures, how does matter reorganize itself? And the conditions have to be so extreme that it's the force of strong interaction, that's nuclear physics, that decides how matter reorganizes itself. So that's what this diagram is trying to capture. So I want you to forget about the temperature axis and concentrate on the density axis. So this is baryon chemical potential, or chemical potential for particle number. So this is basically proxy for the density. So if you take a chunk of matter and keep on crushing it to extreme densities, at first what's going to happen is that ordinary nuclei are going to dissolve into giving you an extended soup of neutrons and protons. So that's nuclear matter. And then every neutron and proton is made up of 3 quarks. And so if you keep on increasing the density, at some point the neutrons and protons are going to dissolve and give you, it's going to give you an extended soup of quarks. And if you're below a certain temperature, And if you are very low temperature, basically, then both sides are going to be superfluid. So you are going to get a nuclear superfluid at lower densities and quark superfluid at higher densities. So this line is below which you have superfluidity. If you go above this line, you don't have superfluidity. So what I want to understand, let's say, as you go from nuclear superfluid to quark superfluid, is there a phase transition separating the two sides? Okay. So why might one care about this? Of course, I don't have to discuss this much. Of course, if you care about neutron stars, you would care about superfluid, dense superfluid matter, right? So here is a cartoon of what I imagine to be the case, one of the possible cases. So what I'm trying to show here is a cartoon of a neutron star. I have almost eliminated the crust here. So what you see here, this is the outer core, this is the inner core. As you know, when you're looking at neutron stars, in the outer regions, you have lower densities. As you go inside, you have higher densities. So it's sort of like you're traversing this x-axis as you go inside the core. Okay. So one might imagine that you have nuclear matter superfluid in the outer core, and in the inner core you have quark matter superfluid. And let's say your star is rotating around some z-axis, which goes upwards on the board. So you could imagine having superfluid vortices that carry on from one side, go through nuclear matter, then go through quark matter, then come out from the other side in nuclear matter. And so I'm showing you this picture because I will have some comments on this on these vortex structures inside neutron stars. Okay. So now let me tell you quickly what we know about what happens in nuclear matter. So this is what is expected. You have condensation of dibaryons, so it could be 2 neutrons, 2 protons, and so on. So I'm calling them dinucleons. So that NN operator picks up a non-zero vacuum expectation value, and every single nucleon is made up of 3 quarks. So there is this corresponding 6 quark operator that has a non-zero expectation value. So Q stands for quark fields. Okay. And remember that every single quark field comes with a color and a flavor index. Now, inside this nuclear matter, however, there's the diquark fields, like two quark fields, do not have non-zero expectation values. Okay, so that's what we expect inside nuclear matter. And this dinucleon object breaks particle number, U1 particle number spontaneously. And that gives rise to superfluidity. Now, what do we expect inside quark matter at high density? So you have a Fermi liquid of quarks. Okay, so you have a Fermi sphere. There's a BCS instability at the Fermi surface, which gives rise to Cooper pairing of quarks, just like what you saw in electromagnetism, okay, or superconductivity, ordinary superconductivity. So you have a bosonic diquark condensate, so QQ is not equal to 0. And you can use mean field theory to show that because this QQ is not equal to 0, the 6 quark operator is also not equal to 0. So you have basically 2 scenarios. Let me compare the previous slide with this one. The previous slide, you had the 6 quark operator that was non-zero, but this diquark operator was 0. In the other case, the diquark operator is non-zero and also the 6 quark operator is non-zero. So this problem, what I just showed you, can be actually mapped to even a cleaner problem, simply because I'm going to deal with either the diquark object or the 6 quark object. I'm not going to deal with individual quarks, so I'm going to map to a different problem, which is cleaner. So again, you have the SU3 gauge theory. Take with it a U1 global symmetry, and on top of that, add fundamental representation scalar fields and 3 of them. Okay, so you can combine these fundamental representation scalar fields into a single 3x3 matrix. So let's say the rows tell you about the SU3 index, right? So that's the SU3 gauge index, and the columns tell you the flavor. So you have 9 entries for the single field, which is capturing three fundamental representation SU3 fields. Okay. So if I wanted to transform this under SU3 gauge symmetry, all I would have to do is to, let's say, multiply by an SU3 matrix on the left-hand side and nothing on the right-hand side. Now, this also transforms of the U1 under a U1 gauge symmetry like this. So what is this phi? This phi stands for the diquark operator, basically. So as I said, this diquark operator is a bosonic condensate. So that's what I'm trying to write down here. Okay. Now, okay. So this is what I was just saying. Inside high density, phi has a non-zero vacuum expectation value. Inside low density, phi has no vacuum expectation value. Now, in both regimes, however, determinant of phi has non-zero expectation value. Because if you remember, the 6-quark operator had non-zero expectation value in both cases. So this phi, every single entry is a diquark object. So if you take a determinant, that would be a 6-quark object, right? So that has a non-zero expectation value in both nuclear matter and quark matter. And this determinant of phi breaks U1 global symmetry spontaneously because it corresponds to the 6-quark operator, which is a dinuclear operator. And so this determinant of phi serves as an order parameter for superfluidity itself. Okay. So could you use that diquark object, that phi field, to detect a phase transition between nuclear matter and quark matter? I would say no, because phi is a gauge dependent object.
You introduce the determinant, because actually you have the 6 quarks in the data basic construct the sacred determinant of it. This one you understand. So to make it easier if you mention that.
Okay.
Yeah.
Yeah, I am.
But that's the standard language for more than half a century.
Sure. Okay.
Yeah.
Yeah, correct me as I go through, what
I'm a little confused.
Go on.
This is so
Right.
diquark operator will have
Right.
two color,
Two flavor.
in
This is the color flavor locking, right?
You assume
So you can rewrite the 4-index object as a 2-index object.
So all the color indices these are only the flavor indices outside.
Right. Well, should I write? Maybe not.
you can write on
this?
Yes,
Not with the markers. Though.
not really exactly.
I think it's better to use the blackboard.
Yeah.
So should I maybe do this?
So what is your question?
So her phi.
I think you can write it simpler as a 6x6 matrix.
Okay.
Because you have 6 quarks. But she decided to take couples. And
Yeah,
use the
some
3x3. But that's technical thing. It's convenient for her. You see, why?
I don't know how big I
find out.
This can see.
But that's all there is. You see, it's unusual. You see, it's label determinant. You have 6 triangles, you make it antisymmetric, totally antisymmetric, and that's it.
That is true.
So you're saying that this has, for example, right? Yeah, so I'm rewriting this by defining this another object, which is
Because it has to be antisymmetric.
Yeah.
That's it.
so that's the channel. That's what I'm doing. That's why it has one color and one flavor.
You can group 3 of them together.
What about the sextant?
You see, and you'll have triplets, and another triplets, and then you have nucleus.
Yeah.
You decide to have that. So that's not the only way to do it, but
Right.
why you want to do this.
Yeah. Okay.
So, you see,
Yep.
low density nuclear matter, you have triplets.
That's
And then she goes to high density because it's going to be.
Maybe that's why it's called conjecture and continuity between the two.
Yeah.
It's a 6x6 determinant. You see, that's what you remember. You see, if you partition it in different ways, that's not a big change.
So
It's still 6x6.
okay. All right. So this slide is done. Yeah. So can you use phi to detect phase transition between the two sides? Well, no, because this is a gauge dependent thing, and to use that is not a reasonable thing to do.
That's like the regular phase of the wave function.
Yeah.
It's exactly the equivalent of that, nothing else. Yeah. Which you can make local or make it global.
Yeah. In this case, it's global.
Yeah, in this case, it's global. But that's what it is. There is no deeper meaning into that.
So the only gauge invariant local order parameter at our disposal is determinant of phi, and that is non-zero on both sides. Okay, and transforms under U1 symmetry. So you can't use that to detect difference in a phase transition. So that's something I already said. Now, if you actually did the analysis, if you actually counted number of massless modes on the two sides, you would see that they match up, unlike ordinary superconducting. Also, you can't do an explicit calculation.
Why do you say that in the superconductors you don't have the same number of modes? You say that superconductor is gapped. Actually, it's not gapped. You have sound modes. And they are all, no matter whether you're a superconductor or not. You see that they start from zero. It's a continuous spectrum. So the spectrum is not gapped. It's the fermionic branches is gapped, but the total spectrum is never gapped.
Well, the gauge field is gapped, right? The gauge field is gapped.
Well, I probably say, can I excite the system with arbitrary amount of energy, no matter how small? Yes, I can.
Okay, so
not in a superconductor.
Yes, yeah. I can. I have sound waves. I have sound waves, and they start from zero, then infinite wavelength.
Is that true?
Yes.
Of course it is. You see, you can knock on a superconductor, the sound propagates.
Well,
so it's always there.
Isn't it true that all correlations go down exponentially, decay, and so on?
There are two types of excitation.
That's not true.
What do you mean it's not true?
In a superconductor, well, what is the sound in a superconductor? It's not what you think sound is in a superconductor. No, that's the mass of the photon.
There is no photon.
That's a different one. That's the plasma. You have plasma modes and you have regular sound waves, like in any charge system. Sound modes exist always. You never destroy them.
Which sound? Well,
yeah.
Let's come back.
The spectrum exists,
right?
So
that doesn't exist. Okay, let's come back.
No. There is nothing to come back. You see, don't confuse. You see this spectrum. You see this mode. And phase starts from zero. Okay. No matter what the system is.
So what is that excitation that has that spectrum? What is it?
It's
excitation on top of what? What field?
On top of the ground state. What do you mean? So
the condensate.
I can make the thing vibrate.
Okay.
We'll come back to this.
Okay.
You can make vibration with that.
I'm sure you are.
No, you're not sure of anything.
All right.
It confuses plasmas. This one you confuse.
Okay.
Plasmas indeed have a final gap.
But
that's not the sound waves. Those are the different mode. They're called optical branch and the sound branch.
So
this is regular solids.
So you can't do a explicit calculation either. So if you actually did, looked at the modes and so on, you would see that there is continuity.
One comment. Your second question there is the equating of all the sound modes.
I'm sorry.
The second statement is that all the Goldstone modes, all the sound modes match. All these number Goldstone modes.
In this case,
on both sides.
Yeah.
So
he said in a superconductor.
Yeah.
Yeah, so that.
You see, she said that you have gap below. Or you see, she said that below.
The gapless modes.
He's talking about superconductors, I think.
Yeah.
So
Okay.
Let's not. I think my remark was correct.
All right. So there is the Schaefer-Wilczek conjecture, which says that quark matter and nuclear matter are smoothly connected because of this. Okay. So, however, we have known for some time that phase transitions are not always accompanied by change in symmetry. This is one example, the VKT transition. There is a fractional quantum Hall effect, neither of which follow the symmetry paradigm. So there are multiple things to do if you wanted to detect other kinds of phase transition. One set of phase transition that you could try to probe is topological phase transitions. One thing you could do is to put your theory on a compact manifold, compact space-time manifold, and analyze it. And I'm not going to do that in this talk. Equivalently, you can look at probes like vortices and flux tubes and compute Aharonov-Bohm phases. So we are back to our original starting point. So this is what I'm going to do for quark matter. This is where I can really do a calculation because the theory is weakly coupled. So I'm going to look at vortices inside quark superfluid. And there's going to be a color magnetic field inside the core of the superfluids. And so what I want to capture is the corresponding Aharonov-Bohm phase. And now, because it's an SU3 gauge theory, the gauge field is a 3x3 matrix. So once you do the line integral and exponentiate, you have to take a trace to get a number. So that is the object that I'm going to compute. And this phase around vortices is going to serve as a new tool for detecting phases for my talk.
Can you measure them?
Yeah, if you could make a color superconductor, you could, right?
Is there any weight? How do you measure that? How do you measure the phase?
Like what kind of setting you're imagining?
The omega you see which are out there.
Right, so you would have to do an Aharonov-Bohm experiment, which would be possible inside quark matter, right? So it's like an experiment inside a medium.
It's not clear how to do it. Yeah, that's what I'm saying. You see, we go to LHC.
No, yeah. So no, not in our world. It almost like, yeah, because we are outside of quark matter, we're not inside. So that's the problem, right?
Well, I don't know. Anyway.
Okay, so here are vortices in quark matter. Picture is the same as I showed you before. So I'm going to solve for vortex profiles in quark matter. The R got behind the picture, sorry about that. So again, I have to write the energy density for quark matter superfluid, and it's the diquark object that makes an appearance. So I have to take a covariant derivative of this diquark operator, mod square, and then take a trace. I have to take a trace because phi is a matrix, so that's why there's a trace. And this A field now is a linear combination of the SU3 gauge fields. So I'm going to declare that that's the cheapest vortex ansatz that you can write without a loss of generality. So it's a diagonal object. And delta is the strength of the condensate. Only one of the entries carries a winding. And this radial profiles F and G, they go to their asymptotic values far away from the core of the vortex, which is where really I'm going to do the analysis. Similarly,
that it has a structure.
I can argue about some of the parts. Probably can't
Is
be
it a mathematical statement or what you're saying?
I will come back and try to address some of this, how to decide that's true. So similarly, there is the ansatz for the gauge field, and this is what you see, it's the 8th generator of the SU3 group. You could play trying to write down various linear combination, but again, you have to trust me that this one is the one that minimizes the energy density. So just like the parameter B that I had in superconducting case, I have the parameter A, which is what I'm trying to figure out by doing the energy minimization. So now, I will come back to your question. Just let me finish this slide. So if I write down the energy density, what happens is the following: when the gradient term hits this phi, it produces just single derivative in the first entry, and everything else is 0. And this is the gauge field. And this is what the energy density is. There's a square here, which I forgot before taking the trace. So this is what you get when you write down the energy density. And if you minimize it with respect to this little a, you would find that it's 1/3. Now, one very important thing is the following. If I substituted a equals 1/3 in this energy density, you would see that it is at its minimum, but it's not 0. Okay, so it's an order 1 number over R squared, And that has to be the case because really I'm talking about superfluids. So this is a superfluid global vortex. So that's why you see that. Now, let me try to motivate the ansatz for the condensate that I wrote a little bit. So number one point to notice is that the determinant of the phi goes as e to the I theta. So I told you that determinant of phi is really the superfluid order parameter. So if I wanted to make a superfluid vortex, I would have to have the determinant of phi going as e to the I theta around it, around the axis. So now phi has to be single valued. That's why I cannot, have fractional windings on the entry. So that's why only one of the entries is to carry the full winding.
But I think what people call the hug vortices is exactly that case where both components have a phase and the sum is fixed.
So they don't come back to themselves?
Not each component. You see, are you familiar with the hug vortex monobig? You see, I think that's the case.
I think they're third vortices here.
Say it again.
I think there are third vortices here and 2/3. There's 3 components.
Doesn't matter. You have only 2 components. You'll have half vortices, but then you'll have phase in two elements, not in only one. That's what I'm saying. You put the phase in the first, put the phase in the second, and the combined phase is the entire thing. Because when you take the product, you'll see only the sum of the phases.
So you want to put e to the I theta over 3 on every single one of them?
No, you put I theta and you put I phi on the next one, and you quantize the sum.
So e to the I theta plus phi you want to make.
Yeah, this one.
Why?
Because this is the only thing which you'll see actually in your phase. See what you see if you take the.
So I think the thing you want to do is you want to put them all 3.
You can do
and
3.
then
In this case, you can do 3.
When you get back to the previous state, the overall wave function is changed by an overall phase, but that's irrelevant.
This is exactly what happens here too. You see, because you take the determinant of that, it's only phi or theta.
Theta, yeah.
But basically, it's actually the phase of all 3 is the sum. You see, this is the only thing which enters. You see, the only difference is instead of having
right. But if you have a macroscopic wave function for phi, right?
I think you see that I'm correct. You see, when you have 2 components, you see, you can have a half vortex, and in this case, obviously, you have a different type of vortex too. So I'm not sure you see this same mistake.
What I'm trying to say is the following.
I understood what they're doing.
Okay.
But there is another thing. You minimize only the kinetic energy.
Yeah.
You don't minimize the energy density. Because in a vortex, actually, the amplitude goes to 0 at the core of the vortex. In your case, it doesn't.
What do you mean? It does. F and G do go to 0.
Condensate will go to 0.
Yeah.
Condensate has to go to 0 because
look at the image. It is 1 over r squared.
This is far. I think far. This is
no,
far away.
Go
this is far away from the core of the vortex.
No, you see that this is what it is. 1 over r
I think
squared.
everything is far away. I think
everything is far away.
The condensate has to go to 0. Otherwise, it's not unique value. So
yeah.
And how it does that is dependent on the microscope.
Yeah, I don't know how it goes linearly or something. I don't know that, but it has to go to
in
0.
3 dimensions. The 1 over r squared arithmetic cancels with the polygon. So I don't think that's important, but I think. But
this is far away from the core of the vortex.
You minimize this locally, not globally. You see that.
That's okay. That's all you have to do to find out what the gauge field is.
It's not how I calculate vortices, for example, in Fermi fluid, in Bose fluids. You minimize the total energy, not energy density.
Right. So that will tell you what the profile is, right? So this is like asymptotically far away. Yeah.
I think maybe if I'm understanding correctly, her goal here is not to solve for the profile,
right?
Just to find the value of A.
Yeah.
And the winding, the flux.
That right.
Far away from the.
Yeah.
And she only needs the far away solution.
I just need the flat connection. That's all.
And you can numerically solve the profile and all that stuff.
I mean this has the numerical solution has been done by other people. So all right. Okay, so
but
this.
You didn't explain the aids. You explained only how you get the 1/3. But can you explain the gauge field with that structure? You simply had an ansatz, for the phi.
You mean I didn't?
Yeah, you didn't explain why that is that particular structure.
Well, you can try to write down other things, and then we'll have larger energy.
Okay. So if you write other things, you run into troubles. You say.
Yeah, they will cost you more.
Okay, so this okay.
All right. So, oh, another important thing I wanted to mention. What is it? Okay.
Sorry about that.
Don't worry.
But, yeah, I want to understand.
It's okay. You stay for long.
Don't mind it.
So I just want you to contrast this with superconducting and superfluid. What is this ordinary superfluid vortex? You said you saw that the energy density goes the same way, but these vortices are also somewhat like a superconductor because you have the gauge field. But the difference with ordinary superconductor is that in case of ordinary superconductor, the winding of the condensate is completely absorbed by the gauge field, right? And this is because your condensate is a U1 valued object, your gauge field is U1 too. In this case, the difference is coming from the fact that this is not an SU3 matrix, this is an U3 matrix. It has to be U3 so that determinant of phi can come back to itself. If it was SU3, determinant of phi would be just 1. However, the gauge field is SU3. So the U3 object's winding is not being able to be absorbed by the SU3 gauge field. If you had an U3 gauge theory, then it would be able to absorb. And so that's what's going on here. That's why you get the superfluidity or superfluid vortex by writing this kind of solution. Okay, so now you compute the Aharonov-Bohm phase by doing this line integral. And what you find is that the phase is e to the plus or minus 2 pi over 3. I haven't written minus here. Really, plus or minus depends on whether you're computing the line integral in the direction of the superfluid flow or opposite to the direction of the superfluid flow. So that's what I'm trying to capture here. The link, this L is the linking number of this path along which the vortex is with the path along which you're computing the Aharonov-Bohm phase. So if you're computing this along the direction of the superfluid flow, this L is positive, +1. If it's opposite, then it's -1. And if you're not going around the vortex, it's 0, so you get a 0 Aharonov-Bohm phase. So this Aharonov-Bohm phase is actually experienced by a single quark field. If you were to shoot a quark quasi-particle through this color superconductor, you would see this. Just like the pi phase in superconductors is seen by an ordinary electron. So that's what's going on. Now, there are some new kinds of baryons that you can define in the system, which will have, as a consequence of this orbital, as a consequence of this non-trivial Aharonov-Bohm phase, they will have fractional orbital angular momentum. So one way to make them is the following: take a probe quark, which has a single color and a single flavor index, combine it with a condensate, which has also single color and single flavor index. So contract the indices, you get a color singlet baryon, which is a nucleon. So this is a 2 quark object, that's a single quark object. So the whole thing has 3 quarks. Now, what do I mean by fractional orbital angular momentum? So this is what I mean. So let's take these fancy baryons. So in the absence of any vortices, they behave like normal baryons. So let's say you don't have a vortex and you want to create the orbital angular momentum eigenstate, the orbital angular momentum operator that's pointing in the z direction, let's say. So that's big LZ, okay? And so its eigenvalues are going to be little lz, which are integer quantized, and the energy spectrum is going to be related to this orbital angular momentum eigenvalue as Lz squared. So it's going to be n squared, where n is an integer. Now, if you create a vortex along this z-axis now, the spectrum is going to change, okay? So in that case, the energy of these eigenstates are going to be related to the orbital angular momentum eigenvalue in this fashion. So they're going to be shifted by ±1/3. So that's what I mean when I say orbital angular momentum is fractionalized. Really, the spectrum has changed. So now I'm going to do a comparison with low density nuclear matter. So in the nuclear matter regime, first of all, phi, the condensate, is 0. So remember that in both ordinary superconductors and the quark matter side, it's really this macroscopic di-electron or di-quark object that pinned the gauge field to its value far away from the core of the vortex. So that is what is providing the Aharonov-Bohm phases. If you don't have that, then nothing pins the gauge field far away. And so it fluctuates strongly. And if you computed the Aharonov-Bohm phase, you would get a phase of 0. And so omega would be 1. So if that's true, then there has to be a phase transition between quark matter and nuclear matter that is detected only by this kind of non-local order parameter. Okay. So there is a little bit of a consequence for the kinds of vortex pictures I showed you inside neutron stars. So let's say you have vortices going from nuclear matter to quark matter. Now, on the quark matter side, a single quantized vortex is going to have 2 pi by 3 Aharonov-Bohm phases around them, and inside nuclear matter, they don't. So what one would imagine at the interface between nuclear matter and quark matter, 3 vortices have to come together to make a Boole jump that then go on to the other side, so as to avoid, a discontinuity in the Aharonov-Bohm phases. So the vortices don't connect directly between nuclear matter and quark matter. So that's one entertaining consequence. Now, here are some of the questions that I wanted to ask you, and also I'll tell you what I'm working on right now. So first of all, you have any thoughts on if these kinds of non-trivial Aharonov-Bohm phases around superfluid vortices and quark matter can have an effect on turbulence, for example? Also, the fact that you have these Boole jumps, can they affect how vortices interact with each other and so on? The thing that I'm working on is, for example, the following. It is possible to engineer very similar situation using electromagnetic U1 gauge fields. So I'm trying to design 2 superfluids that are undetectable using symmetry properties, like the Landau paradigm, but you'll be able to detect their difference or the sharp difference between them by looking at Aharonov-Bohm phases around vortices. So, so I will just need a U1 gauge field, charged and neutral scalar fields in order to achieve this. So this is what, well, we have almost finished the paper. We're just trying to put this out right now. So the question is this kind of model, can it be realized in cold atom experiments, or maybe using multi-component superconductors, something like that? So these are the questions that would be nice to get an input on. So, all right, so that was the end of my talk. Thank you. It was finished before time.
Additional questions?
There's enough questions to think about. Can't answer any more.
Any answers? So you need some sort, if you want to do this in cold atom experiments or something, you need some gauge symmetry, right?
Yes.
So you need to look at something with maybe, dipole atoms or something where there's.
Should be like flavors.
Yeah.
The notion is that if you have fermions with 9 flavors, you're going to have collapse.
No, but you don't have to have 9 flavors here. I mean, you
No,
actually
just
this in,
3.
No. Look at part 2.
But this I don't need.
So she's trying to find smaller examples.
So I need, so the model that I have a multi-component superconductor really. I have charged scalar fields with plus and minus 1 charges that couple to another superfluid, which is a neutral scalar field.
I have a small question here. I would like to see 1 point couple the quark with the phi. See there, and you made the new type of barrier.
Mm-hmm.
See that one.
Yep.
But I thought that all quarks are already paired.
Right.
Why do you have single quarks? That's an excited state there.
This is an excited state. Yes, these baryons are.
I mean, so you have quarks, so because if you have that, you probably the entire system has color.
Yeah.
You see, so you have a color.
That phi.
No, the entire system, global. I mean, the global. The system,
no. That's because you have three flavors, right? So.
But then it will have color only on average 0, but it will fluctuate from point to point.
Yeah.
And that's a very unusual.
That's color superconductivity, right? So.
Well, so it's a highly excited state, I think. You have great pairs.
Oh,
To have three quarks.
Yeah, the quark has to be above the pair.
Yes,
it's the pair, yeah.
But it's highly excited, you see, think, and by the way, it's stable.
So.
You see, if I do this in a regular fermionic superfluid, it's very hard to create that unless I have spin imbalance. But if you have spin imbalance, it's the same thing with I'm saying you have color imbalance.
Mm-hmm.
Then you have a C meta, which I think is very hard to create. I don't know if it exists.
In color superconductors, you should be able to, I mean, they are not going to be completely stable. So you will break pair and then they'll form a pair back again.
I mean, like in a neutron star at low temperatures, you wouldn't have these.
Yeah, that's true.
What?
This would be your experiment that you're trying to do, or during formation or at high temperature.
That object, I don't think it can create physically.
What do you mean? Yeah, I mean, you will have to supply certain energy to break pair, right?
But then once supplied that, the system thermalizes, and then what is the system really?
Well,
you see, if you break pairs, if you have lots of energy put into the system, what about
you have to break a single Cooper pair, right? So that's not going to be disrupting your whole system.
Well, that's another question. See if you can do that, and then use that in excitation. See, I don't know. You see, because you can think of an excitation like that in a regular superconductor. You see, you break one pair, Cooper pair, and then combine that with that. You see, I don't think anybody ever saw a system like this. But that's simpler than this. I don't think anybody considered that type of excitation. So if a station like this exists, it should be seen there too. It doesn't. Don't need many colors and flavors.
Well, there is one thing there, because if you create an electron, you break a pair, you cannot combine it with the condensate to make a gauge invariant object. So here, for example, this Q5 thing doesn't transform under color, right? So it's a little bit different. So I'm not sure how to.
Yeah, your gauge invariance. I criticized the very beginning.
It's a color neutral object. That's what I mean, right? So a single electron in a superconductor, that's not a color neutral object, and you can't combine it. Sorry, it's not electron. Sorry, it's charge neutral. Yeah, that's what I meant. That's right. So I don't know how to compare that particular aspect of superconductivity with this. By the way, the fact that this kind of, you can combine quark with the condensate to write these kinds of baryons, this is really not something I came up with. This was Thomas Schaffer and Frank Vortices.
Well, if you go to nuclear physics, you find a so-called IBM model by Achille, where everything is reduced to bosons. So we describe low energy spectra to boson, S and D bosons, D wave. And then you go to odd nuclei, where you have an extra fermion, and then you have supersymmetry, and you have objects like this. But because there you have one extra fermion, because you have odd nuclei, see, odd number of protons, odd number of neutrons. And there you have a theory of that. You see, there is a ferrological theory, it's exactly that object. So, like as my professor when I was in undergrad said, every new thing, it's one forgot another thing. So this is one of them. So look at the supersymmetry in nuclear physics. If you look at Frank Achille, you see he combines fermions and bosons together and constructs and that's it. That can be measured.
Okay.
So it's measured. So those objects exist.
I see. Okay.
So you are talking about this cold matter.
Yes.
So how much density do you need to get this thing?
It depends on, but yeah, a lot. Yeah.
Maybe the core of a neutron star.
Yeah.
Maybe more.
There is a maybe. Yeah. Yeah. I mean, there are some models that say that, if you have a chemical potential of 700 MeV, 600 MeV, you might be able to get. But those are model calculations. So I don't know to what extent you should trust.
The picture becomes accurate at really high density.
Yeah.
No one knows what that is.
these flux-tubes are not related to grids. So, I mean, there are no.
How do you know that? How do you know that the flux tubes aren't related to glitches?
I mean, we heard that I mean interaction between both proton flux tubes and neutron vortices cause some pinning.
Right.
But in this case, we have some mechanism.
Well, so the picture is here.
It would be these bosoms, right?
Yeah. So the bosoms happen here. The same vortices would be pinned here, I'm guessing, which I haven't drawn. Right.
Where would the
cross fit somewhere
where
else.
would the color crystalline fit?
Not sure.
On the red line.
On
the red line?
On the red circle.
Okay.
Well, thin region in the LA.
Before the neutron nuclear superfluid, I guess. Yeah, you're
No,
right.
after
So right where the bosoms are.
Yeah, right where.
So there are these phases that have crystalline structure. The loft essentially phases that have been predicted. So they live somewhere on the boundary, I guess, that inner quark. So where these bosoms are. So they could cause that was the original model, was that the quark vortices would pin on color superconducting phases.
I see.
Is the division between the nuclear matter and the quark matter, is that actually a sharp division, or is this something where there's sort of a evaporation fraction of the nuclei?
So I'm not sure about the answer, but I think what we are saying in this talk is that it is a sharp division.
You're arguing there's a phase transition.
Yeah.
Well, but you're arguing that sort of after, but isn't that after you already assume that you go from actually having neutrons and protons to having them break up into quarks, or?
Well, so there are two. The claim is that they will break up between quarks, but earlier people believed that it was a smooth thing.
Okay.
Even if you break up, it's a smooth thing, it's not a transition. But we're saying that that's not going to happen. It has to be.
Maybe I can say something. So it depends. So there's no symmetry breaking, so it can't, you could say that it's not second order, but it can be first order, and in most models it is first order.
Mm-hmm.
In which case, you will have the same story, that you'll have a mixed phase at this red boundary.
Why is first order? What's the argument? Apart from her argument.
No, her argument doesn't tell about the order.
No, I understand. No, but she says that it's a fake because she has an order parameter.
In fact, her argument will say that it's zero order.
It's
zeroth order. There's no discontinuity in free energy parameters. But there's no symmetry breaking, so it can't be second order, the Landau paradigm.
I believe it's not even a phase transition. It's a crossover, like plasma, going to plasma.
It could be, but in most models, you get a first order transition.
Do you have model applied to plasma to see if we can do the same thing? See, try the first example, you see plasma. Do you get a crossover?
No.
And probably you won't, because you use mean field and that's wrong.
Yeah,
this usually both is the first sort of line critical endpoint. You can get a crossover if you go around it. There's usually all sorts of things when you don't have.
So ordinary superconducting transition is what, second order?
No, the high temperature thing is first order.
It's first order.
There's no order parameter, so it can't be.
Right.
There's no justification for a second order transition.
Right.
It could be smooth, but it turns out to be first order. Mean field gives you second order, but it's first order. So here also, just on general principles, it will be first order. That means there'll be a mixed phase and all the past stuff.
So I see. So in case of superconductors, right, the gauge dependent thing, that does it jump across the discontinuity, or so it doesn't go smoothly to
it doesn't. It doesn't go to zero smoothly. There's a first order transition. It's very weak because
weak first order. I see.
How do you know
Well, the calculation, there was some calculation by Gorkov or something, and then it might have been measured also.
So, but if I look at just the abelian Higgs model, I think that is going to have a second order phase transition.
In perturbation, in what do you call it?
Yeah. So in
Mean
perturbation
field
theory, in mean field theory, yes.
Mean field
yes,
theory
second-
will give you second order.
Right.
Fluctuations can shift the energy. So
Yeah. Okay, I see. So that's what I was thinking. Okay. There is a corresponding story here as well, where you just think about scalar fields and don't think about fermions at all. And that's, there is the Higgs confinement continuity story of Eduardo Fradkin and Steve Schenker, where you don't have to think about fermions and so on. So there it could still be a second order phase transition, I think. But I don't know about it, whether it is or not.
And that's non-perturbatively solved?
Yeah.
Yep. Okay. Any other final questions for now? All right. Thank you very much.
Thank you.